I'd like to talk now about the next few review problems, starting with review problem 1.9. A cereal company puts a prize in 95% of their boxes. If you buy one box every week for a year, so 52 boxes, what is the chance that you collect at least 50 prizes? So the probability of at least 50. Well, the chance of at least 50, there are three possibilities. You could get 50 successes, or you could have 51 successes, or you could have 52 successes. Now let's figure out each of these in turn. This is a binomial experiment, or at least it's basically a binomial experiment. There is a fixed number of trials. You do something 52 times, and the chance of success is 95%. There's also a well-defined notion of success and failure. Success means you get the prize, failure means you do not get the prize. The central problem is counting the number of successes. The only slight detail is that technically it's not independent. However, if you have a cereal company that puts out billions and billions of cereal boxes, then essentially it is independent, even though it's technically without replacement. So, because I have such an enormous population, I will treat this as effectively independent. So the chance of 50 successes would be 52 choose 50 times 0.95 to the 50th times the chance of failure, which is 0.05 to the second. N choose r, pi to the r, 1 minus pi to the n minus r. So that's 50 successes. For 51, it'd be very similar. If you have n choose r, 52 choose 51 times 0.95 to the 51st times 0.05 to the first. And finally, for the last one, we have 52 choose 52 times 0.95 to the 52nd power times 0.05 to the 0th power. In all cases, the exponents add up to 52. I've got the probability of success to the number of successes I want, the probability of failure to raise the number of failures I want, and there's a binomial coefficient representing the number of possible ways that that could happen. Okay, so I'm going to do on the side here off screen this calculation. So I'm just going to be typing in the what you see on screen into the computer or into your calculator, and then it's just a matter of punching in and hoping that we don't make a mistake when typing in. So almost done here. And finally 0.95 to the 52nd power, and I get a chance of about 51%, so approximately 0.5146. It turned out for this one it was not advantageous to invert, meaning that at least 50 is the opposite of less than or equal to 49. But clearly it was a lot less work to do 50 or more, just adding these three numbers up, than it would be to do 49 or less, which would be 50 numbers being added up. So here it was more advantageous to add directly. Okay, the next problem, we've got a typo, but let's just go with it. Two cards are dealt from a wild shuffle deck. Find the probability that the first is an ace or the second is a jack. So the probability that the first is an ace or the second is a jack. Okay, this is an OR question. Before adding, so we're going to add, but before adding we ask ourselves, are the events disjoint? The events are not disjoint. It is perfectly possible for the first card to be an ace and simultaneously for the second card to be a jack. And so I will add these two probabilities, the probability the first is an ace plus the probability the second is a jack, But as I'm writing now, we have to subtract off the probability that they both happen. The probability that the first is an ace and the second is a jack. Okay, so for the next step, it'll start off very much the same as before. So I'll just copy it. First line starts off the same. The probability the first is an ace, plus the probability the second is a jack. Then here I have an AND question. For an AND question, I multiply. But before multiplying, I ask myself, are the events independent? In this case, they are dependent. What happens on the first card will affect what happens on the second card. So I have the probability that the first is an ace times the probability that the second is a jack, given that the first was an ace. Okay, now let's do these problems separately. The probability that the first card is an ace is 4 out of 52. The chance that the second card is a jack is also 4 out of 52. If I do not look to see what the first card is, and there's no assumptions about the first card between this parenthesis and this parenthesis, then the chance that the second card is a jack is 4 out of 52. Minus the probability the first card is an ace is 4 out of 52, times the probability that the second card is a jack, given that the first is an ace, and the chance of that happening will be 4 out of 51. Now notice that this fraction, 4 over 51, is different than this fraction, 4 over 52. 4 over 51 is a conditional probability, the probability that the second card is a jack, given that you know the first card is an ace. This fraction, 4 over 52, comes from here. This is unconditional. There are no assumptions about the top card between this parenthesis and this parenthesis. And so I just simply have 4 over 52 for this fraction. So finally, we need to figure out what the sum of those fractions are. So 4 over 52 plus 4 over 52 times 4 over 52 times 4 over 51. And this works out to be approximately equal to 0.1478. The last problem I would like to talk about now is problem number 11. Suppose 1,000 raffle tickets are sold, and 50 of these are winning tickets. So you have a good chance of winning. There's 50 ways to win in this game, and you purchase 10 of them. Let X be the number of winning tickets that are purchased. What is the chance that you get 2 winning tickets? This one is hypergeometric. There is a certain number of tickets. There's 1,000 tickets, of which 50 of these are good tickets that I win. And there are 950 tickets that are quote-unquote bad, in which I lose. I purchase 10 tickets in this raffle. The question is, what's the chance that I win 2 prizes, that 2 of these tickets are winners? So if I win with 2 of the tickets, clearly the other 8 are not winners. So the chance of 2 winning tickets is going to be found by the hypergeometric formula. Here I'm drawing without replacement. There are 1,000 tickets in this game, and I choose 10 of them without replacement. So I have the chance of winning is going to be 50, choose 2, times 950, choose 8, all over 1,000, choose 10. The total number of good tickets, and I choose 2 of them, times choosing the number of ways I can choose them, 8 tickets from 250, divided by the total number of ways of choosing tickets, which is 1,000, choose 10. So once again, it's just a matter of plugging into the calculator to figure out all these binomial coefficients, and then figuring out what this fraction is. As always, if you get an answer that is less than 0 or bigger than 1, it's incorrect. It's a probability, so I have to get a number between 0 and 1 out, and I get 0.0743. So that's the chance of getting 2 winning tickets. The next part of the question is to find the mean and the standard deviation of x. For this, we will plug into the formula, so let me clear this off. The expected value of x, the expected number of tickets that are winners, will be equal to, well, I chose 10, and the chance of winning on any one ticket is 50 over 1,000. And so I get 500 divided by 1,000, or 0.5. So I expect to win 0.5. Let's now figure out the standard deviation of x. This computation has 2 square roots. The first square root is very much like what appears in the binomial distribution. It is n times pi times 1 minus pi, where pi is the fraction of good tickets there are. In my case, 5%, 0.05 of the tickets are winners. However, because I'm drawing without replacement, I have this finite population correction factor. So 1,000 minus 10 over 1,000 minus 1. Capital N minus little n over capital N minus 1. And because I have these numbers, even though 1,000 is much bigger than 10, I will use those numbers when I compute. The first square root here, involving 1,000 minus 10 over 1,000 minus 1, that's a number that's going to be pretty close to 1. But because it is given to me, I'm going to go ahead and use it. And so plugging into the calculator to see what this number is, I get about 0.686. And so there is the mean and the standard deviation for this random variable.